Bienvenidos, welcome, welcome. On behalf of the University of Illinois system, I thank all of you for your participation in the Quantum Computing and Microelectronics Technology, Driving Innovation in Modern Industry Symposia, hosted by the University of Illinois System Mexican and Mexican American Student Initiative. I-MMAS, we call it I-MMAS. Through I-MMAS, the University of Illinois system conducts extensive research and student exchange with several Mexican universities and government agencies. I believe right now we have close to 500 people registered, and all of you are very welcome to this very, very intriguing symposium. I-MMAS was built on the idea that when we connect students, researchers, and institutions across the border, both countries are stronger for it. I'm Elvira de Mejia, a professor and founder of I-MMAS and is Director of Institutional Relations with Mexico. Muchas gracias, colegas, colaboradores, estudiantes, profesores, instituciones en México, por colaborar con la Universidad de Illinois, por confiar en nosotros, por ser nuestros, nuestros partners, decimos acá, ¿verdad? Ser nuestros colaboradores y amigos en este importante evento. I thank the speakers. The speakers are a group of very talented professionals from Mexico, from Illinois, and elsewhere. It is a great team. Event speakers will examine that quantum technology means for industry, for the workforce, and for the next generation of scientists and engineers in the United States and Mexico, and how partnerships between universities and industry can accelerate technology innovation. Quantum technology will shape the careers of the next generation of scientists and engineers. We will witness benefits on energy, savings, fuel, medications, climate, food, to mention a few. The speakers include Jeremy O'Brien, co-founder and executive chairman of C Quantum, the company anchoring the IQMP campus. Dr. Jeong, head of quantum computer at Pascal USA Inc., which is established its US headquarters are IQMP. Speakers leading quantum computer researchers from prestigious institutions, our own Dr. Harley Johnson, the executive director and CEO of the Illinois Quantum and Microelectronics Park, and a founding professor in the Department of Mechanical Science and Engineering, University of Illinois, Champaign, Urbana-Champaign. We also have researchers from Mexico, from the Center for Nanoscience and Nanotechnology at the National Autonomous University of Mexico, the Center for Research and Advanced Studies in Bestap, the National Polytechnic Institute, and the Tecnológico de Monterrey, Mexico. As Illinois Quantum and Microelectronics Park centers around collaboration, we hope that this symposium will bring together research universities, industry partners, and global quantum leaders to work together towards a common goal, advancing and commercializing quantum computer and innovation. The objective of this webinar is to promote strategic collaborations among the industry and the University of Illinois system in the areas of quantum computer, microelectronic technology, industry, and innovation. The symposium will open with welcome remarks from our distinguished Dr. Jay Walsh, Vice President for Economic Development and Innovation at the University of Illinois system, also by Dr. Rashir Bashir, Dean of the College of Engineering at the University of Illinois, Urbana-Champaign, and the ambassador, our dear Mrs. Reina Torres Mendívil, Consul General of Mexico, la Cónsul General de México, la embajadora Reina Torres Mendívil. So we will get started with Dr. Jay Walsh.
Thank you for that wonderful introduction. And welcome to the Symposium on Quantum Computing and Microelectronics Technology, where we're driving innovation in modern industry. This is a timely and important conference as we see the acceleration of research and development activities in quantum technologies worldwide. Research into quantum physics and associated quantum technologies is not new, with formative work being done more than a century ago. But like many fields, advances in this field are stochastic. Great leaps happen after time when new technologies or new approaches are gradually developed. Quantum devices have been in our hands for decades. Quantum communications and computing are in that great leap phase. During this symposium, we will hear both about the buildup and certainly about the current great leaps in quantum technologies. In no small part, the University of Illinois, most specifically the Granger College of Engineering in Urbana-Champaign, have played a huge role in this build and propelling phase. When one looks back at the 13 physics Nobel Prize winners from UIUC, one can argue that each one of them is founded in quantum science and technology. This history of excellence, of innovation, and of impact on society has been profound, and there is no doubt that it is continuing to this day. In the most obvious way, we now see the growth of the Illinois Quantum and Microelectronics Park, IQMP, a first of its kind campus built on quantum technologies and microelectronics, innovation, and scale up. The park is strategically located on the south side of Chicago, frankly, at a very beautiful lakeside location. It's 12 miles from downtown Chicago, about an hour from our two international airports, thus easy to travel to, and less than 2 hours from our two national labs, Argonne and Fermi, which alongside Northwestern, University of Chicago, UIUC, and UIC, that is University of Illinois Urbana-Champaign, and University of Illinois Chicago, form a group of large and impactful research institutions with a strong history in material science, physics, and computer science, all of which are vital to the growth of quantum science and technology at IQMP. This is matched by local R&D strength with numerous industries that are joining and indeed in many ways leading our efforts at IQMP. The memorandums of understanding we have with our Mexican organizations represented here today aim to strengthen collaborations between the University of Illinois system, i.e. its universities, its faculty, its students, and its researchers, and with our wonderful colleagues from Mexican organizations. The objective of the symposium today is to promote strategic collaborations among industry partners, the University of Illinois system, and our Mexican partners in the areas of quantum computing, microelectronics, technology, industry, and innovation. There is a particular emphasis on the importance of partnerships in addressing challenges and shaping the future of quantum. If you are here today, you are invited to become part of this effort. If you have colleagues who could not attend today, tell them what they learned, what you have learned, and indicate to them that they are welcome to become involved. If you are a student, this is an exciting time, this is an exciting area, and you too are welcome. Partnerships are key to the advancement of the work you will hear today. We welcome you to become partners. Finally, a quick note to our speakers and panelists today. You are a group of very talented professionals from Mexico, from Illinois, and elsewhere. Thank you for your time and talent. And one final call out to Hai-Chi Chen at the University of Illinois Springfield. You bring tremendous energy to all that you do. You brought many ideas to today's event, and I personally thank you for all that you've done to help build this symposium today. Back to you, Elvira.
Thank you, Elvira. Good morning, everyone, or good afternoon, depending on where you are and which part of the world. Buenos dias to all of our friends and colleagues for joining us today from Mexico. It's a real pleasure to welcome you to the symposium on quantum computing and microelectronics technology. Let me begin first with some thank yous to Elvira. Thank you so much for your vision and leadership in founding I-MMAS and for building these bridges that are just so important across our two great countries, and what makes this gathering today possible. To Dr. Jay Walsh for your partnership across the Illinois system, across the UFI system, and also to Ambassador Reina Torres Mendevil. Thank you so much, the Consul General of Mexico in Chicago. Thank you for your presence this morning and your steadfast commitment to strengthening the ties between Mexico and Illinois. I want to tell you why I'm so genuinely excited about this moment and why I believe the symposium is also exactly at the right time. So we are standing at the threshold of a new era of computing. Quantum computing, quantum technologies are moving out of the lab and into the marketplace. This is starting to happen and is happening as we speak. And you'll hear about this a bit later today, of course. I actually also recently wrote about this in an op-ed for the Chicago Tribune. And I wrote about the spirit of collaboration that is so important and that has actually powered every transformative technology of the modern era. Today, it is defining the future of computing itself. And I think, we should really make no mistake and think about this. I mean, this is what is at stake here, is that what will the world look like 78 years from now? And I say 78 because that's when the transistor was invented. It's been about that long when the transistor was invented, and look at where we are today with the advances in microelectronics and Moore's law and computing and AI. Quantum is that next revolutionary breakthrough technology that is going to change the face of computing. Quantum will not replace traditional computing. It will work side by side, and it will solve some very important problems that you'll hear about today. Quantum is not simply going to produce a faster computer. It is fundamentally a new way of processing information, an entirely new math that needs many more new algorithms. The one thing I'll mention here is this little story that began in 1981, actually at the University of Illinois Urbana-Champaign, where Sir Anthony Leggett and his student Amir Caldera. Tony Leggett was a Nobel Prize winner. He actually passed away just about over a year ago. And he asked whether the strange rule, at that time, strange rules of quantum mechanics could survive the scale of real circuits and real machines. So he posed this question back in 81, and they had a paper that was published that proposed that could quantum mechanics be observed in macroscopic circuits. And last year, that question, was recognized. I mean, the answer was recognized with the Nobel Prize to colleagues from UC Berkeley and UC Santa Barbara, who then did the experiment that demonstrated that. But that original question actually has roots back here at the University of Illinois. The futurist Roy Amara is another name. Maybe we can look him up. So he observed that we always, there's a thing called the Amara's law now, that we always tend to overestimate a technology's impact in the short term and underestimate it in the long run. When the web browser was written, which by the way was the first web browser was written here at the University of Illinois Urbana-Champaign at the National Center for Supercomputing Application, people said in 5 years it's going to change the world. Well, it took about 20 years or maybe 25 years to change the world. So I think the point is that we have to keep an eye on the long run and really work on what's important and work on all the important critical problems so that we can have this impact in the medium and the long run. The engineers who built the first transistors, they weren't immediately promising the smartphones. They were trying to make a more reliable amplifier, right? A better device. And I think this is really what we need to kind of keep in mind, is that if the history of computing is any guide for us, the second half of Amara's law is the one that will also really matter. Quantum computing will transform how we discover new medicines, design new materials, secure our communications, and understand our world in ways that we cannot yet fully imagine. So our job in these defining early years is to work with industry, as you'll hear later as well, who are really advancing the technology and getting to that goal of a fault-tolerant quantum computer, and at the same time keep working on improving the various aspects of that technology food chain, right? Make sure that the science, the hardware, the algorithms all keep improving. Even though microelectronics is, half a century old, there's still research in advanced microelectronics, right? So that's the idea, is that there's tremendous opportunities in advanced research in quantum technologies. And I will end that by saying that a very important piece that we need to work on together is the workforce. We need, above all, the ecosystem, which is not complete without the workforce. This is so important. We need many more talented students of all ages to come together and work on these great new technologies. We need to go back to the basic. This is an opportunity for the mathematicians and the math department. This is an opportunity for chemistry, computer science, of course, electrical engineering, computer engineering, hardware. All of these areas are going to be really, really, really important. And Illinois, this ecosystem is taking physical form at the IQMP, which we'll hear later about. I'm super excited and thankful that Professor Jeremy O'Brien is here, co-founder of PsiQuantum. They're our lead anchor tenant for IQMP, and we're just so thankful for their partnership. Also, you'll hear from Dr. Harley Johnson, IQMP CEO, who's done a phenomenal job of advancing the park of where it is. So we're also here in Illinois building the ecosystem. And as I say, for generations, researchers from Illinois have invented the future. And we have watched it flourish elsewhere. So this time, we're hoping to keep the ecosystem, build it here, and of course, share it with the world and share it with our partners and work on this together. And I think this is exactly why this partnership is so important and matters so much, because no single institution, no single company, and one would argue no single country will build this technology alone. So Mexico and Illinois are natural partners, are natural partners. We share integrated supply chains. There is, hemispheric semiconductor opportunities. And like I said earlier, most importantly, our people. Mexico has extraordinary talent capacity. And as today's program makes it clear as well, with leaders from many great universities. So through I-MMAS, we're committed to growing that talent pipeline together because the quantum and the semiconductor industry will need hundreds and thousands of skilled scientists, engineers, and technicians in the decade ahead. And I didn't mention the semiconductor workforce needs. They're also great and also immediate. There is tremendous opportunities in that space as well for us to work together to produce the talent workforce. So my hope for this morning is simple, that this symposium is really not an endpoint, but a beginning of joint research, of students and faculty exchanges and industry partnerships from both sides. So I hope we can keep pushing forward. And there's a saying that if you want to go fast, you go alone. But if you want to go far, you go together. So I would add that let us, be quantum mechanically entangled together and go farther. So thank you all. Muchas gracias. And on behalf of the College of Engineering at the University of Illinois, welcome and enjoy the symposium.
Gracias, doctora de Mejia. Thank you so much, everyone, Dr. Welsh and Dr. Bashir, for your words, and particularly to those who had this incredible initiative. Doctora de Mejia, You are not only a good friend, but a great partner. I really appreciate what you have done and what you are doing, trying to strengthen the partnership that you have, that the University of Illinois system has with Mexico, with many important institutions in Mexico. And actually, I appreciate that today we're convening to talk about quantum and the future of our region is well, of course, it's tied to the future of quantum. Dr. Bashir said it very clearly. We're in the threshold of a new era in computing and a new era of the way we do things. And as in many other important scientific developments, we cannot stay behind. And it's important to have these partnerships, to talk to each other. And in this particular case, what the state of Illinois is doing, developing this incredible ecosystem to favor the development, the research, the construction of quantum computers, and to further research all the uses that the humanity can have from this technological and scientific developments is incredible. So I really congratulate all the institutions that are connected today. I see a large number of people connected in this symposium, and I congratulate you because you are in for a treat. This is not only fascinating, but is incredibly relevant in our world. And I just want to say a few words on what Mexico is doing. You know how important our partnership is with the United States in many areas, but also in this one. You know that nowadays we are one of the main suppliers of computer service to the United States. We are already a key element in the ecosystem that provides traditional computers to the US. So we can be now on top of what is being developed in terms of quantum. We have the institutions in Mexico that Dr. Bashir mentioned, all the talent that is going to be needed to develop this ecosystem here in the state of Illinois, and Mexico can also play a key role. It's not only important to have those exchanges and to spread knowledge, but also to be able to exchange talent from both countries in this particular area. So I commend all the universities that are here connected and that are also partners with the University of Illinois system. Just a last word about the potential of collaboration. Sometimes we tend to think that, you know, countries like Mexico or some other countries that perhaps are not in the top of the research in certain areas cannot participate of initiatives like the one that is created here in the state of Illinois. And that is a myth. That is not right. You know, and particularly in the world of science and technology, you know that science come from other spaces that have nothing to do with, you know, the position the country plays in the economy or other political considerations. So that's why this symposium is very important, and the fact that all of you are connected here is really important. Take advantage of what you're going to discuss in this event, and I see a lot of opportunities, a lot of exchanges coming out of it. Gracias a todas y todos, felicidades por estar aquí conectados y les deseo el mejor de los éxitos en este importante evento. Gracias mil, doctora de Mejía, y gracias a I-MMAS.
And now it's my great pleasure to introduce Dr. Hei-Chi Chan. He's the Associate Professor and MSP Department Chairperson, Mathematical Sciences and Philosophy, University of Illinois Springfield, University of Illinois Springfield Artificial Intelligence Campus Learning Community co-founder. He is the co-organizer and moderator of this symposium, and the idea was given by Dr. Hei-Chi Chan for this symposium. So we will be always grateful for that. Dr. Chan, let's get started.
Okay, let's get this started. Thank you, everyone. Hey, our first speaker is Dr. Jeremy O'Brien. Dr. O'Brien. Hi.
How are you?
Good. And today we are going to do a fireside chat with you. And so glad to have you here today, Dr. O'Brien. You are the co-founder and the executive chairman of PsiQuantum, and in fact, the longtime CEO of PsiQuantum. And so glad that you can be here today. And
Thank you very
so
much.
and what most people know you are a founder of this company, a company that is one of the top native quantum company in the world with a valuation over $7 billion. And you guys have raised over $2 billion. But long before that, you established yourself as an expert in quantum computing. And in fact, you have a strong collaboration with Professor Paul Kuick in Urbana. And so how did your early work that set the stage for everything that you are doing and building today? Help us to understand that.
Yeah, sure. Well, thanks very much. I'm very excited to be here and delighted to share some what sound like now very old memories of my time at UIUC in Paul Queer's lab. Actually, I guess it was 25 years ago, or a little
Something
more,
like that.
maybe even. Yeah, so I started here in Australia, where I am now, working on various different approaches to quantum computing, including phosphorus donor spin qubits in silicon. But also I looked at, gallium arsenide quantum dots and, superconducting systems and organic conductors and various different things that I was exploring. And one of the ideas that was really central to that work was the idea of manufacturability and leveraging the semiconductor industry ultimately to make a large-scale quantum computer. And the way I remember it is that I was pretty young back then, whatever that was, 25 plus years ago, and I was, that seemed like a very neat idea to leverage the semiconductor industry, but how could you do it? And I couldn't see a path with some of these things that I'd been exploring. And then this idea of photonic quantum computing was invented right around then, and I was extremely fortunate to be able to get a postdoc position with a former postdoc of Paul's. So Andrew White had been a postdoc of Paul Queer's when Paul was in at Los Alamos Laboratories, and Andrew had very recently returned to Australia, and so I was very fortunate to get a postdoc position with him working on photonic quantum computing. And because of his close connection with Paul, I sort of inherited that close connection, and very soon after starting that postdoc was privileged to spend an extended period in Paul's lab at UIUC, and doing some really pretty interesting work actually on I'll spare the technical details, but on process tomography, ancillary assisted process tomography. And then there was a sort of reciprocal arrangement where one of Paul's postdocs came to Brisbane, to the University of Queensland, where I was for an extended period, Dave Branning, and together he and I, along with my colleague Jeff Pride and Andrew and Tim Ralph at Queensland, we implemented this photonic controlled knot logic gate. I guess that was back in 2002 or something like that. So yeah, the very earliest work actually was part of a collaboration with Paul's group and UIUC, and 25 years later, it's really pretty exciting to be talking with you all today in the context of the Microelectronics park. And our position there as a company as the anchor tenant. So yeah, it's a big quarter century circle, I guess. So yeah, I hope that answers the question a little bit.
Well, that's
some of that early
wonderful.
work.
Yes, a lot of history back in Urbana with you and with Illinois, and you're coming a full circle back here. And talk about 2016, that the year that you and your co-founder launched, Psi Quantum. That was a big moment in your life, back then, I remember 10 years ago, the big headline in quantum computing was, hey, we make a 5-qubit, processor. That was the big headline back then. And back then, when you decided to step out of a university research center to launch a company, well, I don't know about you. A lot of people will feel like it's a massive gamble. But looking back today, and walk us through that transition and bring that transition to the vision of PsiQuantum today.
Yeah, so I guess that's sort of, leaping another 10 to 15 years into the future, which is a nice, a nice step. And I guess, that's right. That was the point that my 3 co-founders and I decided to move to Silicon Valley and start PsiQuantum. And it's a beautiful sort of, thought process to, okay, what happened between, when I first went to UIUC and then, and the answer was that we worked, the 4 of us, along with many of our, collaborators and colleagues, we worked on the problem of that one that I mentioned before of how do we leverage the semiconductor industry to make a quantum computer. So we spent a lot of time, in the university research environment working on the hardware and the architecture, and in fact on various different approaches to quantum computing, and started to really focus on this photonic approach. And then around 2015, one of our colleagues, Mercedes Jimeno Segovia, she, as her PhD with Terry, co-supervised by me, my co-founder Terry, and also my former PhD student, and then postdoc of Terry's, and co-founder Pete, along with Dan Brown, who's a professor at UCL, published a paper on a photonic quantum computing architecture that was really the basis for starting PsiQuantum. And we believe that architecture delivered that idea that it was compatible with manufacturing in the semiconductor industry. We were only looking at components that silicon photonic components that already existed in commercial products already to some greater or lesser extent, and so on. So that really seemed like the right moment to industrialize, if you like, to really kind of move into an industrial setting, and pursue the really challenging semiconductor engineering requirements to take those components and get them to the performance levels and refine and improve that architecture continuously. So it was really, I guess, the way I would say it is that we really believed that at that point we had for the first time uncovered a path to realizing a very large scale quantum computer using the semiconductor industry, and that was really it was sort of a no-brainer once we had that we should proceed like that.
Right, that's right. You mentioned a couple of times, this is the way you guys build, the qubits, it is semiconductor-based, photonic components built on existing technology so that you can massively create these, computing capability. And in fact, talking about massive, large scale, capability, PsiQuantum is, of course, we know that you're just building, your target is building 1 million qubits, machines, and you guys are doing, major infrastructure development in Illinois. And thank you for bringing that to Illinois and to Chicago. And how does that infrastructures, that massive infrastructure in Illinois set the stage to bring the world's first utility scale quantum computing system to life?
Yeah, so we're really excited, as you say, to be building some really serious infrastructure in Illinois, on the south side of Chicago, there at the former U.S. steel site. And for me, it's very exciting to be, working at such a historic site that, was really at the center of previous industry, millions of tons of steel produced, contributing to the skylines of this country, of America, in profound ways. And now to be, building the foundations of the future industry is really exciting there. And I think the way to understand it is that we're scaling up these systems. So in fact, you see one of the cabinets in an early prototype form virtually behind me here. Inside of those cabinets, we install large numbers of silicon chips, photonic and electronic, and cool those to very low temperatures. And at the point that we have a sort of million qubit scale machine, then we have a really quite substantial facility. And so we are in that phase now of scaling up that infrastructure. So to be doing that in Chicago is really exciting for us, and all the partnerships and connections that we have, starting in Chicago and emanating outwards across the state, across the nation, and across the world. And I think that's, I think this symposium is a really great example of that, where there's a sort of understanding in Chicago and Illinois that it's a huge part of things and a huge player in things, but it's also a big connector and driving partnerships, nationally and globally. And we heard that in the introduction, the need to be able to work together to bring into reality this technology. So yeah, hopefully that gives you a sort of sense of our level of excitement to be part of the Chicago ecosystem and part of the global ecosystem through Chicago.
Right. Talking about partnership, you guys are bringing, Silicon Valley technology with, Midwest, advanced and robust, manufacturing capability together to build a physical future. And that is awesome. And in fact, what you all are doing at PsiQuantum really remind a lot of us about, the footstep and the spirit of Thomas Edison's. Back then, they were building a electric grid. But right now, you guys are building a grid of compute, a grid of quantum computer. And so for our audience, many of our audience today, they might be in science, business, or maybe even in humanities. What is the single biggest way that this is going, this, massive, utility scale quantum computing facility, how is that going to reshape the world?
Yeah, well, it was interesting to hear Professor Bashir in the introduction discussing, the idea that we often, overestimating what the impact of technology is going to be on the short term and underestimating on the long term. And I guess there's always a question of, what is the time horizon and when did the clock start, etc. But I think that the thing with quantum computing is that there's plenty of good ongoing discussion about exactly what the impact will be when and so on. But I would say that it's pretty unequivocal that ultimately you have a profoundly new capability. And actually, if we go right back to the start of this conversation, that work that I did at UIUC in Paul's group way back when was also a collaboration with Mike Nielsen. Mike Nielsen is, to those in the world of quantum computing, a very well-known figure, and outside maybe less so. But Mike wrote the book with Ike Chuang on quantum computing, which is still the very much the standard textbook and the standard reference book on this topic. And he, he's a very brilliant scientist and a very measured person, not prone to hyperbole and so on. And I always like to quote his statement that, if we were ever to meet aliens, making no comment about whether aliens are out there to be, to be met, and if they are, whether we'd meet them or not. But if we were, then we already know something about them, which is that they're using quantum computers. And that's a pretty bold statement, I think. But the way I understand Mike's sort of justification for that is that, without quantum computing, we're stuck in a sort of small corner of the maths, physics, chemistry, materials that the universe allows, right? Like if there's this full possibility, without quantum computing, you're only in a small subspace of that entire set of possibilities. And so we really understand that to be the case. And then in terms of a bit more down to earth, real world impact, we've heard about the promise in medicine and materials and so on. And this is very profound, and much of that is based on very fundamental, scientific, chemistry and materials and so on. And I think a very exciting area is in the domain of whether you think of it as tackling climate change or, facilitating an energy transition, but the ability to design new materials and new molecules that can be deployed in batteries, in solar cells, and indeed in making much more energy efficient processes across industry. And I think we will see just a really profound impact across that whole domain of energy production, transformation, and so on. But then, so it goes across, healthcare, agriculture, something that's interesting in Illinois and in the Midwest more generally, and, in the US and globally, right? So all of these things are going to, I think the way to understand it, it's a really foundational tool that enables so many more things to be built on top of it. And I think that's why it is really worth our effort and worth our sort of combining forces and collaborations to bring this into reality, because there's so many, profoundly important applications that we already know of, and many more that I think we're yet to truly uncover.
Right. Hey, Dr. O'Brien, thank you for today, your time, able to, speak with us, and we'll do a very quick, Q&A. You mentioned multiple times in your in our conversation about, partnership, because, international partnership. How could international partnership in particular, today we have many partners, wonderful partners from Mexico. How would that international partnership help accelerate this innovation and reduce barriers to adoption of this wonderful emerging technology? How can our Mexican partner, how can we work with our Mexican partner to bring this happening?
Yeah, well, I think that, as maybe is clear, I really see the world through partnerships, my entire life and career, both in academia and in a business as well. I see, investors, governments, customers, everyone, I see them all as partners, right? It's all about partnerships. And, it has been my experience in my entire professional life that, international partnerships are absolutely essential. I've mentioned the example of, the Australian UIUC partnership that was really at the foundation of my work in photonic quantum computing already.
That's right.
Another example that was pretty instrumental in my life, and indeed in quantum computing, was the variational quantum eigensolver. So as you may know, that's been an algorithm that's driven a lot of excitement in quantum computing over the last I guess, dozen years or so. And that's something that came out of a partnership between my research group at the University of Bristol in the UK and Alan Asbury-Guzik's research group at Harvard. Alan is now at Toronto. And that was one of the most exciting collaborations between two quite diverse groups of people, inventing that algorithm, implementing it on a photonic chip, and, really exciting a lot of the world of quantum computing. And these things, that it comes out of friendship, out of, excitement with new ideas, out of hard work, bringing disparate people with disparate ideas together and and I vividly remember that whole exercise with the Asbury-Guzik group and the Bristol group coming together, and this sort of incredible, it was this sort of magic of ideas, bouncing off one another and so on. It was some really exciting, fun, and impactful science that got done out of that. And I've just seen that sort of thing time and time again lead to really important and successful results. And I think my experience, and I think it's familiar to many people, is that you don't always know in advance, how it's going to go, what's going to come of it.
That's right.
But you create these opportunities by bringing those people together. And I think that's exactly what we're here talking about today. And I bet that in 10 years' time and in 25 years' time, we'll be, talking about some of the young people that were at the symposium today that are connected with this network, and the wonderful things that they have done in their careers in a whole new world, if we could imagine in 10 years, and never mind in 25 years' time, the world that these people will have contributed to making. And so it's exciting, and hopefully to do a little bit to inspire them to do so.
Wow. Well, thank you. Dr. O'Brien, thank you for coming to speak with us today. Talk and give your questions. Thank you again. Talking about partnership, we have your major partner as the next speaker. And we are going to now welcome our next speaker, and Dr. Harley Johnson, and who is also a big partner of PsiQuantum. Dr. Johnson is the Executive Director and CEO of the Illinois Quantum Microelectronics Park and the founder professor in the Department of Mechanical Science and Engineering at Urbana. Hey, so Dr. Johnson, the time is yours.
Good morning. Thank you, Hai-Chi. It's very nice to see you. And it's such a pleasure to follow in the program, to follow my partner, Jeremy, and to hear his inspiring words. Thanks also to Elvira for the work together with Hai-Chi in organizing. It's also exciting to hear the remarks from the ambassador this morning, and to hear from Jay Walsh and Dean Bashir as well, who've been just very supportive of the work that we're doing. So it's a pleasure to have a few minutes to talk with you all today. And the focus of my presentation will be to share the story of the Illinois Quantum and Microelectronics Park, and tell you a little bit about how we got here and what we're doing, and think with you about ways that we can further our partnership. Just a brief introduction. I'm a professor at the University of Illinois, Urbana-Champaign, and I've been here at the U of I for 25 years. For the last almost 3 years, I've been involved in leading and setting up the IQMP project. And I've built the team and created the plan for the campus that we're building in Chicago, and I'll share more about that story now. And I'll just add that my own sort of background in quantum goes back to my time in grad school in the 1990s, working on silicon quantum dots and some of the early technologies that now are underlying materials and platforms for some of the quantum computing technologies that are becoming industrial tools, or soon will become industrial tools. So to see that happen and see it come full circle is very exciting, and I just share Jeremy's enthusiasm around that. So the IQMP is depicted here in the image on this slide, which is a designer's rendering that shows in the foreground the 128-acre site that is IQMP. It's a massive site right on the shores of Lake Michigan. Jay and Rashid mentioned this in their opening remarks. It's an amazing location that is within the city limits of Chicago, in the neighborhood called South Chicago. I'll say more about that in a moment. In this image, you can see in the background the downtown Chicago, and in the very near foreground, you see some buildings that are labeled PsiQuantum. I'll show you the status of construction on the park and the progress that we've made, and then I'll be happy to answer questions as I wrap up. The IQMP is a campus, essentially. It's a new campus that we're building that has been created to support scale up of quantum technology and some of the related microelectronics R&D that supports it. We're focusing largely on quantum computing. That's, of course, the theme of the symposium and the remarks so far. Focusing on quantum computing and creating facilities and space and infrastructure for companies like PsiQuantum, our anchor tenant, to grow their operations and essentially industrialize or commercialize the technology that has grown up out of the university labs and out of other R&D labs. So this is not intended to replace the university labs, but really create a space for the next generation of technology that will continue to grow and scale up. The site, I want to say a little bit more about the site here and just share a couple of thoughts on the history. So we are building this campus in South Chicago on the former U.S. Steel Southworks steel mill site. The U.S. Steel site was in operation for over 100 years, from the 1890s until 1992. And it at one time was the largest steel mill in the world, and it played a really important role in the history of Chicago and the history of the nation. And the city of Chicago is a world city, and I know many of you know Chicago, and maybe if you've never visited Chicago, you'll have a chance to visit. I've heard people say before that Chicago is a Mexican city, and there's a rich history and culture that arrived from Mexico in the 1910s and 1920s, largely because of the U.S. Steel Southworks site, because this was a massive source of opportunity and employment, and there was a wave of migration between World War I and World War II that drew many thousands of Mexicans to Chicago, where they created roots and started families and had long, successful careers. And that has shaped the culture of the entire city. So this site, once it closed down in 1992, left a very significant, created very significant loss and disinvestment on the south side of Chicago. And for then the last 30 years, almost 35 years, the south side of the city of Chicago has suffered from disinvestment. And so in addition to creating a place to grow the technology and a place for companies like PsiQuantum to build their businesses, we are very excited about the opportunity to revitalize the south side of the city of Chicago. And this is part of our mission as a public university, working with many, many partners, I should add, and I'll say more about that in a moment. But I wanted to just reflect on the history and what this site means to the city and how it is intertwined with the history of Mexican and Mexican-American culture in the city of Chicago. I also want to just share view of the very beginning of construction of the Psyquantum building. This happened just earlier this year. So February 25th, they began erecting steel on the site. And I was there when, probably on the day that is shown right here, February 27th, with one of the members of Chicago City Council, the alderman by the name of Peter Chico. Jeremy O'Brien knows Peter. Peter represents this district in the city, and he's a lifelong Chicago resident, a proud Mexican American, whose grandfather was the president of the Steelworkers Union when this was a steel mill. His grandfather was part of that first wave of immigrants from Mexico. So I stood with the alderman on the site while the steel was going up, and he was holding back tears because of what this meant for his community, to see a new industry rising up out of the site where his grandfather once worked on the steel mill. So there's just a tremendous history here, and that's a part of the story that we're just so proud of and so excited about. So over the course of about 6 weeks, the building was fully enclosed, and today the building looks largely finished from the outside. Jump ahead to an image that was created this week or last week. Building's largely enclosed, or fully enclosed at this point, and we're excited about Psyquantum being able to move in just a few months. This is an image now, not a designer's image, but an actual aerial photograph of the site. There's a very nice piece that aired on CBS News in Chicago on Tuesday, and you can go to their website and take a tour of the site if you like, a virtual tour, and walk through the building with me and the camera crew. So it's a spectacular site, and I just I'm so excited to share the progress that we've made, and very excited about having Psyquantum be the first occupants of the space. I want to now sort of shift and talk a little bit about the story of how this happened here and how we got here, and then sort of wrap up with some progress that we've made recently on planning the rest of the site. I won't say too much about this, except to say that the groundwork for this project, which is unique around the world, there's nothing like this campus being built anywhere else in the world as far as we know. The groundwork was really laid by the basic science and research environment that we have here in Illinois, and Jeremy knows that well, having visited us 25 years back. This ecosystem involves some very impactful funding from the U.S. government, from the Department of Energy, and from the National Science Foundation. Some of the major quantum centers in the country are based here in Illinois, at University of Chicago, at University of Illinois Urbana-Champaign, at Argonne National Lab, at Fermilab. And of course, the programs are excellent. We're very proud of our programs. The Granger College of Engineering that Dean Bashir leads is one of our nation's top 5 engineering schools. And it's big. And so together with our partners, we graduate tens of thousands of students every year who are trained in quantum relevant fields. And I think I feel confident saying that one of the first things we hear from companies like Psyquantum and many others is that they are drawn to this ecosystem because of the availability of talent. And that's one of the reasons for citing the project here. Many partners. These are just state of Illinois-based partners, but these include all of the major institutions of higher education and the national labs, many economic development organizations, and very importantly, the state of Illinois itself. The governor's office and the General Assembly made this project possible through an appropriation 2 years ago of $500 million, which has been invested largely as an economic development project to bring jobs and opportunities to people in the state of Illinois. So we're very grateful for this support and take very seriously our job, which is to make sure this park is a success and that we stand it up and start to create leverage from that public investment. Just very quickly, I wanted to share with you the breadth of what we're doing with industry partners. And so we talked about PsiQuantum, our anchor tenant, and the work that they're doing to build a utility scale fault tolerant quantum computer using silicon photonics technology. Some other companies that we're working with, first, I'll mention Inflection, a company that is based in Colorado, but moving their quantum computing division to Illinois because of the project that we've created at IQMP. IBM is another major partner for us. IBM, of course, is not a startup. It's not a small company. They will site a quantum computer at the IQMP. And in addition to that, there'll be a lead partner in our National Quantum Algorithm Center. I'll say more about that in just a moment. And IBM has announced that they will set up a branch of their consulting business at IQMP. So IBM Consulting has, over the years, built a major business in consulting around cybersecurity, data science, more recently AI. And in the future, they'll be growing more and more into the area of quantum consulting, where they work with other companies to help companies adopt quantum technology. That IBM facility will employ 750 people at the site, so it'll be a major presence with us at IQMP. To give you a few other examples, Pascal, a company from France, will establish their North American headquarters, and a neutral atom quantum computing system at IQMP. Dirac is a company based in Australia. They will scale up their spin-based, silicon spin qubit-based quantum computing technology at IQMP in a major way. We're working closely with them. Quantum Machines, not a hardware company exactly, but a company that builds control systems that are used by many of the quantum computing companies across the industry, will set up a major flagship hub in Chicago. And so, there are other companies coming and we'll make additional announcements soon. But I wanted to give you a sense of the breadth of this project. It's very much thanks to the first steps taken by PsiQuantum, and then the coordination with which the state and our partner organizations set out to attract other companies to diversify what we're doing at the campus, that we've been able to bring in these partners. And then the other piece of that story is that we're starting now to attract supply chain companies. So companies that are not building, quantum computing prototypes per se, but who are building the parts and the components and underlying technologies, enabling technologies to support the industry. So, for example, 0 Point Cryogenics is a company based in Canada that will establish their first U.S. site at Chicago to support quantum computing customers. Ability Engineering is another supplier. They're the company that's for many years been based in Illinois, but they will expand their operations at IQMP because of the growing quantum industry here. And then there are many, many companies shown on the right. The logos are shown here. United Airlines and AbbVie, BMO, Allstate, and so on, who are members of our National Quantum Algorithm Center. They're working with us on developing algorithms and applications that will run on the hardware that's being built at IQMP. So this is another dimension of our work. I won't say more about that now, but I'm happy to share more information for anyone who's interested. Just a quick view of sort of where we are in building out the campus. We've talked about PsiQuantum's building. That's as big as that is. It's roughly 100,000 square feet. You can see from this master plan that it's really quite a small footprint on the much larger campus. They have a very nice site right on the corner with a beautiful lakefront view. But they're the first building of many, and buildings that are labeled 2, 3, and 4, shown in white, are buildings that are already in design, and we've secured the capital to build these facilities. So, for example, building number 2 is going to be a shared experimental facility with really significant infrastructure that's available to companies to lease. So a company could come in and take a small lab or a bay, 5,000 square feet or 2,000 square feet, and lease space for a time to do R&D work. That building will be operated by IQMP and owned by the University of Illinois. And I'll just mention Quantum Works building number 3 is the site where IBM will have their consulting presence called their Future Now Center, along with other workforce development activities, quantum algorithms work. This is more of an office building for training and for some of the administrative work of the park. So this just gives you a sense of how we will build out the park over the years. This is a long-term project, so we'll be building this out for many years. I've got a few pictures of some of the architectural renderings of these buildings. This is going to be an amazing campus. It'll look a lot like, you know, a university campus, so it's very green. Many parts of the campus will be open, designed, you know, architecturally and sort of in terms of the landscape to match the native, you know, plantings and the natural beauty of the lakes, the lake shore, which is of course very different than what that site looked like in the 1950s, 1960s, 1970s. What'll be similar is that it'll be a major place for jobs and workforce and opportunities for the people of the city. So this is a building we're very excited about, which will be sort of the front door and the headquarters of the park. I want to, before I wrap up, just mention that in addition to the physical development of the site, which, as I said, will take years, and the Sci Quantum building is the first building that will open. But as companies come to join the ecosystem in Chicago, we are creating temporary spaces for them around the city. And so we have a set of locations, some right downtown, others a little bit away from downtown, where companies are already setting up their operations. And then once the permanent space is available at IQMP, we will move them to the campus. So for example, IBM is installing their current state-of-the-art quantum computer at Hyde Park Labs in Chicago, and that will be operational in a matter of just a few months. We've got people working downtown, working on algorithms work. We've got other companies setting up near downtown at a facility called M-Hub. And so there's already quite a bit of activity in Chicago just this year that started as a result of IQMP, and that will eventually become part of the permanent IQMP campus. I want to just conclude by attempting to answer the question how we can work together, because you know, the theme is partnerships, and there were 3 areas that I want to highlight. Of course, there are other things we can do as well. The first is around algorithm development, and I want to you know, encourage everyone who's interested to explore ways that you can work with us on the R&D programs that will build the next generation of quantum algorithms. So that's around our center called NQAC, National Quantum Algorithm Center. Second is in workforce development. And so we're building these training programs, including the program that IBM is establishing, but some others as well, that will prepare students and workers for the many types of jobs that will come out of the quantum industry, not just at IQMP, but beyond. And then the third is in the area of corporate partnerships. And I want to highlight that there's an opportunity to help companies both based here in Illinois and potentially companies in Mexico find opportunities. And that could mean, you know, markets, customers, and talent, both on the Illinois side and in Mexico. So these are some areas that I think there are major opportunities, and we're here and open to working together, because this is how we got here, and this is how we will succeed. So I'll stop there, and there's some links here that will take you to more information about IQMP, and I'm also happy to answer any questions that you have this morning.
Well, so that's me, Salvador Venegas Andraca. Let me start. I understand that I have 1 hour to speak. No, I'm kidding you. It's only 15 minutes, so I'm going to make most use of it. So This is my full name, Salvador Elias Venegas Andraca. I work for Tecnológico de Monterrey, and the topic I'm going to address will be some aspects of collaboration for leadership on quantum technologies between Mexico and the University of Illinois. I'd like to say to start with that if you are interested in downloading this presentation together with some of the papers that I shall mention through the slides, feel free to go to this tiny URL or the corresponding QR. Both elements will take you to the same folder in Dropbox. And if you cannot take this information now, you cannot get a photograph of it, then I'll put it again at the very last slide of this talk. I'd like to thank Professor Elvira de Mejia, Professor Heichi Chang, the organizing committee and the conference staff. Organizing this kind of events is very hard. I understand it because I've done it several times. So I truly thank you for the effort and for inviting me to talk here. I also thank, of course, Tecnológico de Monterrey, the university I work for being the platform for founding quantum computation in Mexico with my group many years ago in 2003, starting with. Very well, sir. I was asked to introduce myself. I'm not going to spend more than a minute talking about myself, so that's me. I work for Tecnológico de Monterrey. I wrote for my DPhil in quantum computation at the University of Oxford. Then I went to Harvard University for working on postdoctoral as a postdoctoral scholar. As a matter of fact, I was at Alana Spurugu 6 group back in Harvard at the time, 2008. And since then, I've been working on a number of topics with my group, particularly basically on the development of quantum algorithms for addressing fundamental problems in theoretical computer science, for example, for trying to find solutions to hard instances of the K-set problem. And we also have some research lines focused on the development of quantum algorithms for analyzing biological data, in particular genotype networks, which is a topic we've been addressing over the last 5 years, and the development of quantum algorithms for cybersecurity. In addition to that, we've been working very hard on building bridges with several parts of society in order to bring them to basically, let me use this expression, to evangelize several parts for society with respect to what to expect from quantum computation, why it is important to invest on quantum computation and in general on quantum technologies in Mexico. And part of this work has been done with the World Economic Forum that I've been privileged enough to be a member of the quantum computing network of the forum for a number of years now. And I shall actually mention some of the papers that we have that I have co-authored with them with respect to the societal and economic impact of quantum technologies in our, well, it could be in global society, in some regions, in some countries, in some industries. I'll address that in shortly. Very well, so that's me. Now, the question I've been asked to answer or try to answer is this one. As quantum technologies move from theory to practice, how can universities and industry collaborate to develop talent, research capacity, and innovation networks that position Mexico and Illinois as leaders of the quantum economy? And the answer is, or one of the answers that I can produce is, we can grow by identifying topics of mutual interest. That is to say, opportunities in which, and this is truly important, in which our strengths and weaknesses complement each other. So the point is to find topics that we both are interested in. We find a business opportunity or an opportunity to grow in general. Could be as scientists, could be as business leaders. And also a key element of this is to identify how we can actually collaborate by complementing each other. So the rest of this talk will be focused on showing you what we do in Mexico, our strengths, some of our weaknesses, and then we can start from that point. Very well, and let me entitle this section Reflections on Quantum Markets and a Quantum Workforce. The development of the transition of quantum technology from the laboratory, from academia to becoming an emergent market of advanced technologies requires the development of several products and services. And that's going to be a complex and long-term endeavor. But in order to be successful in this transition from the lab to the market, as they usually call it, we need to focus on several topics in which actually we can collaborate. For example, on the development of high-tech tools for engineers and technicians devoted to production. The platforms that we have, for example, nowadays for programming quantum computers, they are not, I mean, they are useful, but they can be much better. Writing a quantum program now is pretty much like writing back in the day, back in the 70s and the 80s, writing a program in assembly language, or yeah, pretty much assembly language, or as a circuit, as a matter of fact. Now, developing advanced applications, developing advanced algorithms using that kind of tools is very hard. So we need to develop programming tools, for instance, that actually allow engineers, that allow people to focus on the problems that they want to solve and use those platforms as a tool for that purpose. Instead of having, the tool, the platform, the programming platform as part of the problem that has to be addressed. So this is quite important. We also need to have affordable access to quantum computers, which is a key point in for research groups and entrepreneurial efforts in Mexico. We also need to develop innovative teaching methods. And why? This is because, and this is a topic I'm going to address in one or two slides. This is because the audience, the people who will be interested in becoming experts in different parts, in different sites and fields of quantum technology will not necessarily have the same background. In addition to that, we need to work together in order to identify on a continuous basis new applications and new areas in which we can develop quantum technology. I will mention some of the topics that I find of being of mutual interest, but that list is a work in progress. Is to be developed over and over on a daily basis. Why? Because the reality of our countries change. Our priorities change, and therefore the problems that we might be interested in solving also change. We also need to focus on the development of industrial standards. Let me give you an example. The quantum computers, as it was mentioned before, are expected to work in an ecosystem in which we're going to have supercomputers on digital technology, together with many other technologies being put together like a bundle, for the benefit of mankind in terms of scientific research or engineering applications, financial applications, and so on and so forth. Now, the connections that are to be held, both hardware and software bridges, software connections between quantum and digital technology, those interfaces are still to be developed. They haven't been developed yet. We need to work on it. And the connections that are to be built, both at hardware and software level, are not trivial at all. As a matter of fact, it is indeed my opinion that at least for the software full stack that we need to develop, many techniques are still to be worked on, to be founded. For example, a quantum mechanical version of what we call in the software world, software engineering. So doing that is a work that we can actually focus on together. We both, the University of Illinois, the United States, and Mexican scientists and engineers can work together on the development of those industrial standards. And finally, novel business models. And this is important because the entrepreneurial activities, as opposed to what happens in the big companies world, where there is enough money to work on endeavors focused on development of quantum technology for a number of years. Small companies need money on a continuous basis. Now, of course, in the history of quantum technology, there are some companies that have been very successful, that are, as a matter of fact, growing very fast from being a small company to being global companies right now. But that process, in order to develop all the organizations that we need for all the supply and value chains that are to be developed on quantum technology on both sides, in Mexico and the United States, requires access to money and access to business models that we don't have now. All right, so some examples of topics of mutual interest are natural disasters, the development of models, of mathematical models, the recollection of data using quantum sensors, for example, as for the in the previous days of an earthquake or an eruption, which in the case of Mexico, something that we are very interested in because we have a volcano just next to Mexico City. So collecting all the data by using quantum sensors is a paramount activity for us. It's a very important activity, scientific and engineering activity to be developed and run. The development of quantum sensors for those purposes, together with quantum communication systems and applications of basically quantum algorithms for analyzing data my data is very important to us. And I understand that it should be also important to the United States, in particular in those areas, for example, in California and some other parts of the United States, in which earthquakes happen on a continuous basis. Surveillance is another topic of mutual interest. And to do that, we would need to work together on the development and implementation of quantum cryptography protocols and possibly quantum image processing and quantum computer vision. And finally, a third topic of mutual interest could be the design of molecules for novel medications. That would actually be translated into the development of quantum algorithms for optimization, for solving optimization problems. Now, let me skip this one because now I want to get right here on education. Both the University of Illinois and Tecnológico de Monterrey focus, and many organizations that I shall be mentioning shortly, are academic institutions that are focused on teaching and research, but with the ultimate goal of bringing education to our societies. Now, the quantum workforce, or the people who will be members of the quantum workforce, will be, of course, many of them will be young students who will choose to pursue a career in quantum science and technology at both undergraduate and graduate levels. But together with them, coming along, there will be other people who will be interested, or who are right now currently interested in learning about quantum technology. For example, seasoned scientists who are considering a career switch from another topic, for example, engineering, electronics, computer science, into quantum technology. In that, I've had a experience working with the SPIE, which is an American organization focused on the development of both research and engineering applications in optics. I've been privileged enough to deliver courses on quantum computation and quantum cryptography for SPIE for a number of years now. And the audiences, the people who attend the courses that I deliver are seasoned scientists who've been working for 20, 30 years in several branches of industry or academic industrial organizations, and who are willing to learn about quantum technology because they find many overlaps which can allow them to go further to pursue different paths in which they will find economic progress and personal development. Now, the conditions, the assumptions that we can have for training, for bringing education on quantum technology to that kind of audiences, of seasoned scientists, is very different from the assumptions that we can have with young students. Young students who are reading for a BSc or a master's or a PhD in quantum technology, we can assume that they are full-time students. While in the case of seasoned scientists, people working in industry, they will have a very limited amount of time and different financial circumstances. And furthermore, they will have possibly different methods for learning. So putting all these different conditions together will bring us into the development of new methods for teaching these audiences. Finally, with respect to this topic, I would like to show you this slide in which we have 4 different ways to write the very famous hello world. We can use assembly language, which is what we have here on the left-hand side of this slide. As you can see, there's a number of lines that have to be written only to get on the screen hello world. In Python, it's only one line, of course, one code line. If we want to use Minecraft, which happens to be a Turing complete language, we can also do it. We can basically, what I mean here is that we can write programs using serious games, or we can go to ChatGPT or any other LLM and ask them to give us the code for writing, for the code for hello world. Now, the point I want to make here is that there are different tools. Of course, there are different tools for achieving the same goal. But in quantum computation, these tools are to be developed yet. So focusing on that, it could be a topic of both mutual interest for the University of Illinois and Mexico, and could also be a really profitable activity to work on. Well, I don't know how long I still have left. Would you mind telling me how many minutes I still have?
You have 1 minute left.
Thank you very much. So all this information can be found in this paper that I wrote for the Pontifical Surrey Academy of Sciences at the Vatican, and some papers that I have co-authored with the World Economic Forum, in which we address in detail some of the topics that I have just talked about. Finally, the Quantum Mexican ecosystem is composed by a number of different academic institutions working on both experimental and theoretical aspects of quantum information. I would say, well, this is a list of some of the key members of our community. In particular, as speakers, we shall have Professor Fernando Rojas Íñiguez, as well as Professor Wowa Son, Professor Fernando Rojas from the National University of Mexico, and Professor Wowa Son from the National Polytechnic Institute. So this is just a selection of key people working in this field, or different branches of this field. And this is a selection of some of the technologies that have been developed in my country. Professor Eduardo Gomez is the leader, for example, the leader of a portable quantum gravimeter project, which is now at the fourth level of the TRL, and several other projects that I mentioned here. They all can be found in this document, which is written in Spanish, but I'm more than happy to translate it for you in English. And this is a summary of several projects that have been carried out on both experimental and theoretical sides of quantum information science in general, and in particular in quantum computation. So that's it. I would like to say simply that we can finish that we can use quantum technology together with many other technologies to advance the agenda of progress, mutual understanding, and generosity between Mexico and the United States. We shall be neighbors for many, many years to come, and the best that we can do for our both countries is to work together. Really, please, my commitment to the development of strong relationships with the United States is a paramount activity for myself and for many other Mexican scientists who are interested in bringing progress and bringing mutual benefits to our societies. Thank you very much indeed for your time.
So thank you for the organization and the kind invitation. So I'm Dr. Song from Quantum Computing Research Center of APN, Mexico. I will talk about a little about the advanced, really, the quantum ecosystem in Mexico. So first of all, I want to introduce the Quantum Information Division, as mentioned Dr. Salvador. This is a division of the Mexican Physical Society. The coordinator is Dr. Santiago Francisco Caballero Benis. The main area of interest of this division is quantum computing and cryptography. Quantum optics, cold matter, cavity quantum electrodynamics, foundations of quantum mechanics. And there is a Mexican project led by Dr. Jose Javier Sanchez. He's from National Institute of Actual Physics, Optics, and Electronics. We see that is in our eye. And another doctor working Research Center for Engineering and Applied Science and the Autonomous Unitary University of the State of Morelia. The lines of research of this group is quantum optics and quantum interpreter, which is an open source tool for quantum libraries. Well, there is another laboratory of the Institute of Physics of the National Autonomous Unitary of University of Mexico, Quantum Matter Laboratory, led by Dr. Rocio Jauleli. In this group, the topic is high precision interferometry for the development of atomic sensors. Another professor I need to mention is Dr. Alejandro Gunoit from the Autonomous Metropolitan University in campus Azcapotzalco. The research of this doctor is quantum information, open quantum systems, atom-photon interaction, Lie algebra applied to quantum mechanics, two-dimensional materials, computational methods for quantum systems. And of course, the Dr. Sabado just talked with you. So he has the unconventional computational lab in the Tecnológico de Monterrey. And another physicist, Dr. Julio, his research is on quantum optical coherence tomography. And in of the same university that I'm working, IPN, another campus, Baja California, there is a Center for Research and Development of Digital Technology. There is a high performance intelligent computing laboratory. The leader is Dr. Oscar Humberto Montiel Ros. They managed some projects just like National Quantum Computing Integration Program using quantum intelligent computing, consolidation of a national quantum intelligent computing ecosystem, training, research, and strategic application. Now, I would like to introduce our laboratory on the quantum information science. Principally, Dr. Dong, Dr. Quesada, and me, and others visiting professors. We worked on some projects like that. I just mentioned some of them. Scientific and technological development in quantum computing and quantum information, quantum machine classification and AI application, and enhancing machine learning through quantum computing for optimal computational efficiency, strengthening cryptographic security through quantum information and artificial intelligence. Actually, we are working on this last two projects. And another visiting professor, Dr. Li from Simba Mexico. She is interested on series of data analysis, machine learning, support vector Z number, Lifnoff method, and fuzzy logic, neural network-based analysis. And a young, excellent researcher, Dr. Roberto de Jesus León Montiel, from Micro and Nano Photonics Laboratory of Institute of Nuclear Science, UNAM. And another visiting from professor from China, Dr. Song from Dalian Jiaotong University. His lines of research is artificial intelligence, big data mining, prognostic and health management, quantum information. Research area of basically are quantum computation, quantum communication, and the quantum cryptography. Of course, all of them is based on the quantum physics. Principally, we are based four quantum principles: superposition, entanglement, interference, no-clone theorem. They are base of our research work. And we offer some course so the students can take this course, and based on this course, they can go ahead to do some research work. The core course is the quantum computing. In this course, we will introduce the quantum computing theory, and then the quantum algorithms, quantum information theory, mathematical methods, in Introduction to Quantum Mechanics. Here I list some publications in the last years. I would like to introduce them because you can see the recent work we have. For example, Johnson mentioned that for their project, the prism development. So here you can see that we have work on the quantum algorithm, for example, quantum version of the KNN classifier based on quantum sorting algorithm and alpha beta hybrid quantum associative memory using Hamming distance and the algorithm QA-OA, which is quantum approximation optimization algorithm. Well, we consider the entanglement phenomena, or without the entanglement phenomena, we study different cases, applications, and we compare the results with the classical algorithms. And of course, we have some theoretical work. For example, we study the entanglement property of different quantum, different entangled states in different celebrating observer frames. Well, and another interesting work is that we don't just study the qubit, and we study the Q-trait. I mean the system which has the three level of energy. It's really interesting. Okay, because we just for the quantum computing development, we just in this step, we want to discover which system is suitable. Classically or traditionally, we use the qubit, but how about the Q-trait? Okay, so we studied a lot of we studied the quantum information, entropy, and different potentials using the under the fractional Schrödinger framework. And another interesting work is that a PhD student is working on the quantum game, okay, using the concept just like superposition and entanglement in the game problem. Well, we have the national collaboration with the UNAM, UAM, and another universities and institutes. And we have international collaboration with the University of UK, USA, Canada, China, Chile, Brazil, French, Germany, Italy, Turkey, and others. Sorry. Okay, from 2017, we have 9 doctorates. You can see the topic of their thesis in quantum information, quantum image processing. This is a very interesting topic that Dr. Salvador mentioned. For 3D model reconstruction and quantum alpha beta associative models, entanglement property for multi-party systems in quantum communication, entropy and its application in quantum communication, metric-based quantum supervised classification algorithm, quantum optomechanical effect of multi-level atoms in a two-mode cavity, and algorithm QA OA and its applications on the combinatorial optimism. Actually, we have 4 students, PhD students. They are working on the quantum games in the study of decision-making models, quantum generative diffusion models for image synthesis, quantum correlation, dynamics in hybrid magno-optomechanical system, and cross-condition intelligent fault diagnosis for real transit bearing. Okay, another masters we got. Okay, I forgot to mention that we have the red thesis and another prize. We have excellent students. For example, here I want to mention imaging classification using quantum machine learning. So here in our library, we try to propose, implement, and to use this algorithm to resolve some problems. So you can see all of the group I introduced, most of them are physicists, and the concerned in physical problem, but in this group, we are working more about the quantum algorithm. Okay, lastly, we have this student. He's working in comparative study of classical and quantum clustering algorithm for clinical ASD screen data. And another student, quantum-inspired pattern modeling for zero-shot coordination. Well, our students is not just concerned in their thesis. They continue to discover or to develop some tools. For example, in Pennyland, we published or we implemented the generalized Dodge user algorithm. And lastly, we propose a new practical quantum phase encoding method. And they joined the works on the diffusion, for example, the quantum computing school, tending to meeting, and others. Well, recently we participate the event organized of the Google quantum team, the IBM event. And in this picture, we are working together with the College of Germany. We are working in a project related to the quantum computation. And we have a beautiful group. In the middle, the picture, this girl is we are celebrating her birthday. Okay, our students. So I want to send a message to all of you that together let's discover a new quantum era. I always say that there are many hidden treasures in this field. So if we can work together, we work hard, we can discover many treasures. Okay, thank you very much. Here I put my contact. You can you can send me an email. We can discuss about the topic.
Well, first of all, I want to thank Elvira and all the organizers for inviting me to this very interesting symposium. So my name is Isaac Hernandez Calderon. I work at Simbe in the physics department. And what I'm going to talk today is about the work that we have been doing in the laboratory of semiconductor nanostructures at Simbe. Simbe is an institution devoted to research and graduate studies. You are invited to look to the website of SimbeStaff. There are many different departments with many different type of research being developed nowadays. So I'm going to talk about semiconductors. Semiconductors have been very important for many technological developments. I don't need to mention many details. And we have observed a very great development in the last 75 years. So if we remember the initial computers that were tons of weight and occupied very big spaces, so we went through the integration of semiconductor in chips in such a way that we have reached a transistor density of around 10 to the 8 transistors by square millimeter. That's impressive. That's a huge amount of transistors in a very reduced area. And we are now evolving to quantum computing. The transistors are very important materials, and it's the field of work of my research group. We work mostly with 2,6 semiconductors. These are materials that have specific properties suitable for quantum materials. In our lab, we work with most of the semiconductors that are listed here in this graph is the band gap and the large concentrated materials. So they can be single binary compounds or ternary, quaternary compounds. So we can work with all of them that cover from the infrared to the UV electromagnetic range. Most of the semiconductors that we work have this type of crystalline structure. So they are arranged in layers of cation and anion atoms. Our main interests are heterostructures, that is systems of several layers that can be applied to optoelectronic devices, and mostly in the form of quantum nanostructures, as is depicted here. The outline of my talk is I'm going to describe some epitaxial growth techniques, mostly submonolayer epitaxy of submonolayer pulsed beam epitaxy. I will describe with some detail. And I will talk about some very interesting systems that we have been working for a long time. These are the ultra-thin quantum wells and ultra-thin quantum dots. And then I will show you some of the results that we have obtained working with quantum wells with unconventional potential profiles. All this will be explained during the talk. And I will finish with a brief summary. In our laboratory, we have as main objectives the design, epitaxial growth, and characterization of semiconductor heterostructures and nanostructures for optoelectronic technologies. We have an important amount of infrastructure. So one system for epitaxial growth is the typical for the molecular beam epitaxy or MB technique, and most of you probably know. And we have developed these other two techniques in such a way that we can make the growth of ultra-thin with high quality optical properties quantum wells and quantum dots. We have characterization techniques to study the optical, electrical, and structural properties of our samples, and also we have a surface physics system attached to the epitaxial growth system in order to study these very thin films. So we have a Revere 32P system for the epitaxial growth of 2,6 semiconductors. It's equipped with 8 effusion cells. It has a red system. Here is the electron gun. Probably you can see here. It's an reflection hidden electron diffraction system that allows us to monitor, to investigate the surface structure of the atoms as they are arriving to the surface. This is very important, so this way we can in real time determine high quality crystalline structure of our samples. Typically, we use for the growth of the films gallium arsenide substrates. Here I'm showing you a clean substrate and one with a heterostructure. In this angle, the photography doesn't look very bright, but we change the angle, we see that we have very shiny, smooth, high quality heterostructures. So one of the systems that has attracted our attention are the ultra-thin quantum wells. These are very interesting systems, and these are extreme exotic systems that are formed just by a few atomic layers. In the case of this, I will use as an example cadmium selenide, zinc selenide quantum wells. We can go from 1 to 3 monolayers. We cannot go to thicker films because the critical thickness of these systems is 3.5 monolayers. So most of the work is done with these ultra-thin quantum wells that, in fact, they are subnanometric structures. And the active material of the quantum wells is cadmium selenide, which is always in pseudomorphic growth under large biaxial compression. So the growth of these ultra-thin quantum wells is done in what we call a layer-by-layer mode. So this is a schematic drawing of the chamber with a sample that is being grown. So we deposit layer by layer the atoms, the different types of atoms, cations and ions, in such a way that we can have control, thickness, and composition of these ultra-thin quantum wells. For this, we must find the precise substrate temperature to avoid condensation if it's too cold, or evaporation if it is too warm. We have demonstrated that we can go from red to blue emission, not only blue-green, as most of people know with these systems. We can go from red to blue with these ultra-thin quantum wells by using cadmium telluride and cadmium selenide quantum wells. So we can cover the whole visible range. And it's very striking, it's very interesting to realize that these very thin structures have an intense and also very narrow emission, highly monochromatic, not exactly monochromatic, but very narrow emission with very, very nice colors. There are many applications for these ultra-thin quantum wells, for LEDs, lasers, and others, but among other interesting applications, one is that we can insert these ultra-thin quantum wells in an N-zinc selenide P gallium arsenide heterostructure that can be used as a solar cell, and by the insertion of these cadmium selenide ultra-thin quantum wells, we can increase the spectral photoresponse by a factor of 50. That was a very interesting result. So the ultra-thin quantum wells, here's an electron microscope picture, can enhance the trapping of photons in a very impressive way. Additionally, using this technique, the submonolayer epitaxy technique, we can grow submonolayer quantum dots. What we want to say with submonolayer, that the coverage, the amount of material that we deposit is less than one monolayer. However, this is not contradictory, the thickness of the regions are of one monolayer. So this is an example of these monolayer quantum dots with a coverage of half a monolayer, of a quarter of a monolayer, and this is the excitonic emission. They emit in the blue range. That's very interesting. And as a curiosity, they are always with a peculiar two-peak structure. This two-peak structure has been the topic of debate for many years because the low energy peak presents a broader width than the higher energy peak. This higher energy peak is due to localized excitons, and in principle, it could be expected that this would be thinner. However, since it's broad, many people has assigned this to structural defects. However, very recently, we have demonstrated that this broad peak, this low energy peak, is induced by donor impurities, that is M-type impurities, in the quantum layers. These quantum dots are very interesting for single photon emission in the case of new optical devices. Now, in a quantum well, we can tune the emission by modifying the thickness of the quantum well or the composition of the quantum well. We modify the composition, we can tune the emission, and we can go from the infrared to the UV. So typically, this is the atomic structure of zinc cadmium selenide quantum well. And this is very well done by MBA and other techniques. However, we would like to do a layer by layer growth, that is cation atoms, anion atoms, in this case, zinc and cadmium, in a fixed proportion, then again, anion atoms, cation atoms. And this was a challenge. How to do this? It's not very simple, it's quite very it's very complicated, in fact, to try to do that. But fortunately, we use chemical properties, the chemical properties of zinc and cadmium, because zinc and cadmium compete in being attached to selenium atoms. So the chemical competition between cadmium and zinc makes that zinc removes cadmium atoms. If zinc removes cadmium atoms, we can use this technique that I will show here in a movie to make the layer by layer growth of these ternary compounds. So here we can see I open the chute in the chamber, and we grow a layer of cadmium atoms, can be complete or incomplete, it's not saturated in this case. Then we open zinc atoms, they occupy empty spaces or even remove zinc atoms. Then we evaporate selenium atoms, and the selenium forms the layer, the anion layer. Then again, we open the cadmium atoms, and you can observe that atoms attach to selenium, but cadmium does not attach to cadmium, so the excess material evaporates. So we can grow a full saturated layer. And now we open the zinc shutter, and the zinc atoms remove the cadmium atoms. Depending on the time that we open the zinc shutter, we will produce a specific proportion of zinc and cadmium atoms. So this technique allows us to grow in a layer by layer mode ternary quantum wells. We have used this for the production of many different heterostructures. The types of the growth process can be found here. So one of the advantages of this technique is that several quantum wells with different composition can be grown in the same substrate without modifying growth conditions. That is, we don't need to stop the growth, we don't need to modify the growth parameters as would be usually done by other methods, and we can grow in the same room, in the same sample, a large variety of quantum wells with different composition. For example, here I'm showing you two samples. Each one has 4 quantum wells with different composition, and we can even reach high cadmium content. This is very interesting because then we can tune the emission in different colors, for example, for their application in LEDs and lasers. And we have additionally the possibility to improve the quality of these materials because they are very homogeneous. Since we grow in a layer by layer mode, we can have a precise thickness of the quantum wells. We have high reproducibility. We have narrow exciton emission, even for high cadmium contents. Here is a picture of an electron microscope image of a system with 3 quantum wells. And the main proof of the quality of these quantum wells is that lasers produced with our quantum wells presented excellent emission properties. And we were told by a US company, we have some contract with this American company. So additionally, we have used then all the experience that we have and taken advantage of the growth techniques that we have developed and our experience in the monolayer at the monolayer level. We can fabricate quantum wells with highly engineered structures. So typically what we do is we say we want to have a heterostructure, a quantum well with this kind of specific properties. So then we made a design that is, we have a methodology, we make calculations, we try to make a design of heterostructure. Once the theoretical results indicate, the calculations indicate that could be a good structure, then we elaborate it. We made the growth by epitaxial techniques and the characterization. And through this cyclic process, we can refine the properties of the heterostructures. And now I'm going to show you then something we have done that's very interesting. That is the growth. Instead of just rectangular quantum wells, we have grown quantum wells with what we call unconventional potential profiles. So I have 3 examples for this. One of them is this type of staggered potential profile. So in a typical quantum well, we would have a rectangular quantum well, but we have the capability of changing the composition of each individual monolayer during real time, during the growth. That's a great advantage. So typically, it's expected that these materials, zinc and selenide, will be useful only for blue and green emission. But by making band gap engineering, we can tune the emission to lower energies. And for example, here, if we introduce a layer in the middle of this, we introduce a layer with higher cadmium content, then we can shift the emission to the yellow. And in fact, I'm showing here an electron microscopy image of the quantum well. We have the barriers here, zinc minus selenide. Then we have zinc and selenide with 2 different compositions in this region. At the size, lower cadmium content, and the center, few monolayers with higher cadmium content. This modification, this very thin layer, makes the whole change and shifts the emission from the green-blue to the yellow. And we have a very yellow emission at room temperature. This is one way to modify the potential of the quantum well. We can significantly modify the excitonic, the emission properties of the quantum well. Another very interesting and sophisticated example of quantum well is one in which we grow a quantum well that has 15 monolayers of thickness, and we can tune each monolayer with a different cadmium composition. So here is the potential profile. It's related to the composition of quantum well. And just by changing the exposure time to the zinc, the fusion cell, then we can change the composition of each atomic layer of zinc cadmium selenide individually. And for example, with this type of quantum well, it's kind of triangular potential profile. How much?
1 minute.
Okay, thank you. We can produce this very intense green laser emission. And additionally, with making a kind of more sophisticated band gap engineering, we can produce a type 2 heterostructure confined type 1 between zinc selenide barriers. And with this type of band gap engineering, we can produce deep emission at room temperature. And for the production of this sample, of this heterostructure, we use 2 different epitaxial techniques, MBE, SPBE, and SMLE. So this is just an example of things we are doing in our group. So before finishing, I just want to thank some of the contributors, partialists, have had many members in our group during years and many collaborations. And nowadays, the current students, Jorge and Jana, are working on new projects related with this ultra-thin quantum wells and quantum dots. And as permanent staff, we have Miguel Garcia Rocha, Professor Miguel Garcia Rocha, and Dr. Francesc Sutar. So just to finish, as a brief summary,
Thank you.
I have this slide. Then, to the precise monolayer level control, ultra-thin quantum wells, quantum dots, and complex engineered heterostructures can be fabricated with optoelectronic properties, with tailored properties for device technologies. Thank you very much.
Hi, everyone. I'm Hee-Jung Jung, Head of Quantum Computing US at Pascal USA. Thank you, organizer, for inviting me to this meaningful symposium today. As an AMO physicist, I've joined Pascal 2.5 years ago and moved to Chicago last October as Pascal became the IQMP tenants. So here in the US, I lead technology-related activities like R&D collaboration, QPU installation, training customer and users, and hiring talents. So my role is translating technical impact to the real-world impact. So when you hear quantum computing, it sounds distant, abstract, or something reserved for physicists in their research lab. But quantum is becoming much more tangible field where science, engineering, software, and industry meet to get some values. So today I'd like to briefly introduce Pascal, our full stack neutral atom quantum computing technologies and their use cases to highlight the current status of quantum computing industry. So Pascal is a full stack quantum computing company focused on neutral atom technology, established in 2019 in Massy near Paris, where our global headquarters is located. It's been 7 years, and this year is a special year for Pascal since we are going public soon, right after the recent Series C fundraising. Pascal was co-founded by Nobel laureate Alan Aspect for his pioneering work demonstrating the violation of Bell's inequality and opening the path for quantum information sciences. So Pascal's co-inventing history traces back to the series of pioneering works of our co-founders by Antoine Brouet and George Olivier Raymond. As an AMO physicist again, I've known them by their research and papers before joining Pascal. So they really demonstrated the building blocks of neutral atom approach. That heritage is important. It means our scalable quantum computing technology is rooted in groundbreaking physics starting more than 40 years ago. But our focus today is not only scientific discovery, it's also about building useful tools so that more people can access our quantum technology to create values. Okay. So far, we've successfully deployed 7 full-stack neutral atom QPUs globally. It means we provide everything from hardware product to software stacks, including cloud access, algorithms, and use case applications. So multiple QPUs run simultaneously across different countries and continents. Okay. Our neutral atom QPUs have been operational and is accessible through Microsoft Azure, Google Cloud, in addition to our own cloud platform. So our QPU platforms are fully compatible with any standard high-performance computing centers, as you see here, deployed QPUs at Ulic, Gency, Chinica, Aramco, and District Q. All we need to do is plug in Ethernet cable, connect cooling water and power, and then turn on our QPU at room temperature. They may look like black boxes, but these devices are active, as you see here in the center. The first customer use case running on their QPU side. It's important to note that these machines are deployed at customers' computing facilities, and it's not lab environment with physicists around anymore. In such data centers, we need to orchestrate workflow across CPU, GPU, and QPU. So we've integrated quantum software stack to Slum, the standard job scheduling tool, by collaborating with IBM Quantum. We've also integrated our technology with NVIDIA CUDA-Q and NVQ-Link. Such optimal combination of workflow enable us to tackle complex problems like quantum material. So recently, Nature article highlighted our quantum simulation of real material and the experimental verification. This material, TMGO, is a rare earth magnet with 2D triangular lattice structure, the spins cannot align in stable direction and remain in frustrated state. Simulating the phenomena on 256 neutral atoms in a lattice demonstrated quantum advantage that cannot be done classically. This is original vision that Feynman had when he proposed the concept of quantum computer. The paper highlights what classical computer cannot do, like quench dynamics, as you see here in the graph, and reduce runtime from 1 week classically to a day on our QPU. Besides, the simulation of the magnetization was reproducible on our different machines, and 5 QPUs gave the same answer. The customer requirement always trigger our technology development up to the enterprise level. We design our qubits, array, and architecture through collaborative work with diverse industries. This schematic illustrates the building blocks of our technology, specifically neutral atom quantum processors. Our qubits are individual rubidium atoms that we control with laser light. So everything happens in the vacuum chamber, as you see here, which has very low pressure corresponding to the pressure you may feel on the surface of the moon, which is 10 to the minus 10 torr. We use tightly focused laser beam optical tweezers to hold and manipulate individual cold rubidium atoms as qubits in ultra-high vacuum. All the technology has been developed over the past decades around the world. To encode quantum information on those atoms, we use additional laser light. So the zeros and one of our qubit correspond to distinct electronic level of those atoms, and we can induce transition between those states using laser light. Regarding the readout, we use a standard camera like EMCCD to distinguish between zeros and ones at the end of the computation. Then why neutral atom? Of course, there are many reasons in addition to the room temperature operation, for example, scalability. We simply add more atoms in tweezer array by increasing the power of the lasers. We already commercialized product spanning more than 100 to 200 qubits. In the lab, we recently demonstrated defect-free operation with more than 1,000 of qubits, and we are moving toward 10,000 and 100,000 qubits along the path to FTQC. Okay, still. So in terms of fault-tolerant quantum computing, neutral atom could provide efficient ancillary qubit cost and architecture, as well as the connectivity, because our atoms can talk to each other in 2D or even 3D space. At the beginning of our logical qubit journey, we've recently demonstrated the first 2 logical qubit use case, solving differential equations. Because the differential equations has many applications in energy systems, fluid dynamics, material modeling, financial simulation, we've found the fact that logical encoding increases accuracy in solving differential equation compared to the physical qubits. The histogram highlights how logical qubits suppress noise and improve computational fidelity. The processor starts by trapping stochastic individual atoms that require rearrangement. Then it comes to quantum processing stage. Then we measure and read the result. The powerful aspect of neutral atom QPU compared to other modalities are the fact that you can use it for digital mode by running the sequence of quantum gates of individual qubits, or analog mode by continuously tuning this entire system's Hamiltonian over time. Simply speaking, the time evolution of systems energy. Analog mode provides near-term business impact by solving optimization problems that our neutral atom array can simulate, such as maximum independence that serves as a common starting point for many optimization algorithms. It is finding the largest set of nodes such that no two selected nodes share an edge. The graph can be mapped onto an array of interacting neutral atom qubits that interact via Rydberg blockade mechanism. So atoms separated by micrometers do not interact in their ground state. However, when they are excited to Rydberg state, typically with principal number more than 50, they become strongly interacting and entangle, allowing only one atom to be excited within certain range. So in this mapping, we treat atoms as a graph nodes, and we represent edges through interaction between atoms. As a result, we can view a neutral atom QPU as a particularly well-suited platform for studying and solving graph-structured problems. So here you see the simplified image of Pulsar Studio, a graphical non-coding user interface. So you can log in today. It's free emulator. So the dots indicates actual array of atom qubits, and the lines represent the interaction and distance between qubits. Below box, we program the driving pulse sequence like the intensity and frequency detuning. On the top right corner, you see the real-time qubit state and solutions. So based on the machine-level library Pulsar, CoolKit is a high-level language for analog mode, enabling quantum applications like optimization, quantum simulation, and graph machine learning. So by precisely controlling individual atoms, we simulate complex physical problems and enable near-term business impact across finance, material, energy, and logistics. So for example, self-reliant mission planning, I'm not going to go through all the details, but this is an optimization challenge. The question was, how do we get the most value out of limited orbital asset? By applying our neutral atom technology to solve maximum independence set problem, we help partner like Thales to maximize completed mission while minimizing the number of satellites required. Similar thing in the telecom area. And then with Crédit Agricole, the investment bank in France, we targeted credit risk scoring, specifically predicting fallen angel downgrade. We achieved identical accuracy, but with a huge efficiency gain by reducing the number of decision trees from 1,200 to 50 and processing runtime from over 3 hours to just 50 minutes. So we could deliver the same insight faster and cheaper, leading the bank to consider full-scale production. Proteins are critical in biology, and their function depends on how they fold and interact with water, which is a key in drug discovery. With qubit pharmaceutical, we use a quantum placement approach to predict most likely water position around the protein and check it to match the experiment.
1 minute.
So, yeah. For developing use case, we provide high-level open source library like this. And then we also offer a Pascal community platform for your classes and self-learning. And finally, here's our R&D and product roadmap up to next several years, including 200 logical qubits with high fidelity. So we are currently developing machines that push the boundary of what is possible. So you can check our roadmap through the website, it's public. So thank you very much for your attention. Okay.
Thank you. Thank you very much for the kind introduction and putting this great workshop and e-meeting together. As we have heard, quantum-centric solutions have uniqueness that cannot be met by any traditional approaches. My group is focused on the hardware aspect of this technology, mainly creating light sources that can be used to excite quantum solutions. So our vision is visible interconnects for scalable integrated optical networks. Now, today, looking at the data center annual electricity consumption as a percentage of the US annual electricity consumption, we see that we are about 7%. So we are using 7% of the entirety of the US energy production for data centers. And continuing with the traditional scaling, traditional computational and data center scaling, this number is going to accelerate superlinearly. Now, this energy, half of it goes to cooling alone, 50%. And about, most of the rest, 36% goes into computation and servers. Now, what's very exciting is quantum computing has the potential to efficiently handle these complex and high-dimensional data sets, as shown by Pascal, that are currently challenging and energy-intensive for today's classical GPUs. Now, looking into the on-chip compute energy consumption, with the years, these numbers have come down. However, still they're a very significant portion. What's also very interesting is looking into the data and moving the data on the chip and off the chip takes 5 to 200 times more energy than the computing itself, which requires a different kind of thinking than traditional means. In our case, in our vision, it means using optical rather than traditional electrical data transfer. So the typical data center configuration is shown here. This is a picture that we are very familiar with. So these are basically called racks, series of racks, and each rack has nodes. So in a typical traditional rack, you have about 4 nodes, and each node has a number of GPUs. A typical case is 8 GPUs. What this means is in this rack alone, you have at least about 32 GPUs today. Now, within the rack, because of the small distance and high bandwidth operation needs, today electrical connection are used. And out of the rack, which is less frequent operations for the computation, optical means are used. Now, the cooling is because of this highly densely packed, processing units into such small volume. And as we scale these number of GPUs to further and further, how are we going to overcome these fundamental bottlenecks? Now, what we propose is pushing the optical into the rack through reducing the losses and increasing the efficiency. So we can do this by studying, of course, electrical to optical conversion, coupling loss, insertion loss, and minimizing all of them so that we can go towards a fully optical data center that is quantum centric, so that we can get the benefit of the quantum approaches. Now, today, there are many great existing approaches. The most common one is silicon photonics. Yet silicon photonics is bottlenecked by the temperature effects, which leads to wavelength shift and crosstalk. Also, because of the nature of the silicon photonics with the existing solutions, the packaging and integration costs are significant. Recent solutions, optical photonic solutions, involved vertical cavity surface emitting laser, or known as VCSELs. These are again a unique emitter. Again, for the in-rack solutions, they come with a large cell footprint. because of the heating of the element and creating the, avoiding the thermal crosstalk, they are basically put separated further and further. And because of the material choice, typically arsine phosphine based materials, they tend to fail at relatively what we call, lower temperatures to what other materials can offer, such as gallium nitride, which I will focus on. And very recently, light emitting diodes, because of their scalability, because of their current use and technology development in the general lighting, has become an interesting point. And these traditional light sources are typically large and they cannot achieve the speed that's needed. So what we do, in our group is basically we are trying to create the next generation photonics. So instead of going silicon photonics or, VEC cells, we are targeting development of micro LEDs so that we can connect the in-rack and outside of the rack communication with a wide bandgap material, gallium nitride based solution that is temperature insensitive and can be 2D arrayed, which cannot be done by existing solutions. So the first thing is creating these unique emitters. So we target, again, blue spectrum or a large energy spectrum, because this is the wavelength where you can ignite the quantum materials for single photon emitters that can be later processed. And scaling has hundreds of steps, and here are some select steps. Basically, we shape and then we passivate the dangling bonds, we open up the passivation and metallize. So we demonstrated devices, the functional devices, indeed as small as 250 nanometer. And here you can see the IV curves of these scaled devices, which are almost ideal, even 250 nanometer solutions. Now, what's interesting is, as we scale these light sources, we show increased directivity, which led to a very close to ideal coupling efficiency without any lens, which is very distinctive feature. And looking into the speed of these devices, again, we have fabricated variety of devices. You can see the devices here going from 100 micron to non-visible to our regular eye. And looking into the diameter going from 100 micron, 20 micron, 10 micron, 5 micron, 2 micron, you can see here the frequency response. So we have achieved about 2.75 gigahertz in a 5 micron device, which has about 95% optical coupling efficiency to fiber optic. And we believe that we can push this towards 3.85 by just optimization ongoing. Now, where does this value stand? So this value basically, in terms of the traditional light emitting diode technologies, and in the visible spectrum, it's currently the world record. And next, what I will show is we can also make a high density array, and I'll show a projected high density array reaching to 12,000 per inch. So now this is the, again, layout individually addressable. So this is the large paths where we can address individual cells. So we are zooming in further, and you can see here a 4x6 array. And here is individual addressable, and we are put here the Prod I in U of I, or Prod I in Mexico. And what is very important in these kind of emitters is their leakage current, meaning are they going to disrupt the electronics? And you can see all of these array elements are below noise floor. The other important thing is the spectral uniformity within the array, which is very unique. And of course, for high power, high speed applications, high injection behavior. And in this case, you can see from going from 50 to 10,000 amp per centimeter square, the wavelength shift is minimal and the device is behaving very well. So what we project and what we'll continue doing is going into the high density projected ratios for these LEDs so that we can demonstrate a terabit per second capacity in these kind of scaled elements. With respect to energy efficiency and compute density, this solution that we propose, Vision, which is a quantum-centric light source and light platform, is currently projected to surpass the silicon photonics and the VCSEL technology solutions. And we really believe that combined with the advantages of the quantum computing software and quantum solutions, this will help us reduce our energy budget for data centers, basically quantum-centric data centers. So again, today, we are consuming already a significant portion of our electricity, and most of them are going for general GPU or electrical-based solutions through cooling. And what we are trying to do is we are going to replace these inefficient electrical copper links with integrated visible light photonics that is quantum compatible. And we hope to achieve through this a 1,000-fold reduction in data center energy consumption, and combined with the quantum aspect, this is expected to reach a million-fold reduction in overall electricity consumption. So our first stage that's ongoing here is creating the critical visible spectrum physical hardware, which is a foundation required to interface with the single photon emitters in the next generation quantum internet. And again, I just want to reiterate the integrated visible photonics for quantum computation-centric approach in data centers. Requires, in addition to these individual light sources, other circuit elements listed here. And we are currently also working with many great colleagues, in the US and across the world to better situate our solutions. So with that, I would like to acknowledge our funding resources and happy to get questions if we have time.
Thank you very much. Good morning, afternoon for some of us. Thank you for University of Illinois for the I-MMAS and the organizer for the invitation of having me. I'm Fernando Rojas. I'm a researcher in the Center on Nanotechnology of the National University in Mexico. We are in the north of Mexico in Baja California. Today, I want to talk about a simple but very important urgent idea, how to make the bridge between the expertise of quantum computing and the people who are keen to learning, because the background is not quantum computing, and how to use these new technologies like the functional prompting. So in this sense, it's more focused in students and what are the meanings. I will talk a little bit about my research in one subject, and then what we can do in terms of the relation of this kind of initiative in terms of the Illinois and Mexicans. Okay, let me move to the next one. So quantum hardware is maturing faster than the institutions, and the people can then train and to use it. On the one side, cloud access to the real hardware, free frameworks, and generative AI can already translate into natural language, into working quantum code and understanding. On the one side, most academic programs still don't have in-house the full expertise and the domain structure, and also the technical dependence on the hardware to explore the quantum computer. Of course, nobody has formally adopted in terms of well-trained AI features. The prompting has a bridge into the field. This is the broken bridge that I'm setting into sight. We have the quantum technology, the cloud, the hardware framework, and we need to train talents, and we need to fill this gap between these two parts. Okay. There is three things that are conversion nowadays. First, the cloud quantum computing, like has matured, IBM, Quantum Bracket, Azure. So any institution can run real circuits without having the hardware by itself. Second, we have a lot of revolution in terms of generative AI, like cloud, ChatGPT, Copilot, and many others, and can be very useful to explain concept and generate simulation, but we have to work with these technologies in a very specific way. And functional prompt built in basically six pillars, I'm going to talk about them, can provide this bridge between the technology and the expertise, in not just one off trick in the sense of I just interact with AI and that's it. No, it uses as an element of Copilot and coworker in such a way that you can learn and you can explore and also you can make research. 3, the democratization of the quantum frameworks. I mean, we have the most common Pennylang, Qiskit, and now Pascal is also have the features in terms of the syntax and documentation to be available, and with well-designed prompts, you can get a lot of help to do quantum simulation of that system and to explore the quantum computing field. Okay. What is the philosophy? Okay, we need to democratize the access to the quantum computing without losing the rigor. We don't intend to trivialize the physics and the mathematics formalism behind it. We need to distribute the ability to explore and teach to our people with the interest and the context, either pedagogical or research, even if you don't have or don't code enough in the quantum language. And it does not require programming in a quantum language at all. This gives you 3 pillars: conceptual empowerment, so people are independent on the technical intermediacy; pedagogical agility, generate material simulation and exercise that can be done in minutes instead of weeks, doing a proper prompting; and inform rigor in the sense that the abstraction of the prompt doesn't skew the critical thinking. I mean, is this the IA doing the right thing? Is the right result? So we need to work in a way that we learn things to be sure that it is doing the things that we wanted to do. So the functional or the 6 pillars of the functional prompting, I think this was very useful for a student. You can use it right away. Is the anatomy of 80% of the commercial use guys use this idea of prompting. Role: who is the expert? Context: what is the background that you want to study? Task: what is the specific direct action that you want to get? Format: how do you want the output to be presented to you? Tone: how do you want it to do it? Student, formal, academic, business, and so on. Limitation: you don't allow hallucination. You need to test twice the results. You need to make this kind of testing in terms of debugging and so you are the programming. So all the things that have to be done in a very specific prompt. So you had 3 levels of the prompting: simple, general search, which is most of the way that the people is using right now. In the level 2, there is more intermediate. You have clear intent and partial context. And the level 3, you master it with these 6 pillars, and then you can provide all the framework to do a very well designed. I have problems with the prompt. Okay, here. Again. So let's put it into the perspective of the pillars in terms of the quantum computing role. What should the ID Act has? This could be a tutor, combines analogy, direct notation, generate code for Qiskit Pennylang on any architecture or simulation in a language. You can use a Socratic mode in terms of there is an explanation. They don't provide the answer. It's just no answer generator, but a way to improve your knowledge about that. The context, well, this is for bachelor's and early graduate students. It can be rigorous and skip analogy if the users already master some of the features in quantum computer, and goes deep without simplifying and connect all the needs that need to be done of the basic fundamentals of quantum computing or the more advanced in terms of quantum machine learning. Thus, what do you want to do? First, you need to classify the requests. I have a conceptual question, an exercise, go to the book, notebook, platform. I did an exercise. I need to be help with that exercise, not in directed answer, but in that of feedbacks to understand better if I'm doing the things right. Each of them requests trigger different routes on action of the AI. All the things seems too generic and too broad, but in practice, it is possible. Something happened with when I put change the slide. Okay. You have the format, you have an analogy, you have one Instagram, you want a software or one application to use it, and so on. You need the tone that you want to have, Socratic mode. Confirms what you already correct before pointing out errors. Doesn't repeat the analogy if you already know that things. Analogy never gives the answer to fix or no. Doesn't rewrite the user full input code. Never mix different platforms and so on. If you want a specific code for an algorithm, limits the numbers of lines, and then you need to say the limitations and the debugging and to see if this is done properly. And this is from basic four-pedal logical methods with AI. The explanatory, which is basically understanding. The simulation, you have tools that help you to do a guide simulation of some environment. The Socratic, you progress in question that led to participant to understand the do's or concept by themselves, and then some sort of evaluation. For example, and this is the quantum coin to teach the Deutsch algorithm, and it's done from the perspective of explanatory and simulation, and then you go through all the details of the algorithm, and also the idea of superposition and interference, destructive or constructive, to solve a problem is done in a simulation with the waves that are already there. So it increases the ideas of how usually we learn in an environment of education. So we have to do a loop going from conceptual explanation, analogies to connect with our experience, guide simulations, run code, and then apply to real hardware. For instance, and in the bottom, I have a very summarized prompt that I use to generate a quantum variational algorithm for two qubits, and then string with that data which are in Archivo CS over there. How to load the data, how to embed the quantum feature, how is the encoding, what is the ansatz, how many layers, what kind of optimizer, how the output has to be presented, and to present the circuit diagrams and so on. I use this as a training tool, and then it is very useful because it provides a lot of understanding. Of course, we need to give to the student or the teacher or the basics of the quantum computer, the basis of quantum machine learning and conceptual, in order for them to generate a proper prompt using these 7 skills. I've been doing a lot of teaching with the local university for the professors, with seminars, with courses. In Peru, I will give you fundamentals of quantum computer, and now we are going to do like an introduction to this idea of generative AI and functional programming to do quantum computing from training to quantum machine learning. And this institution or Association of Higher Education and Information Technology have done course virtual, and it's practical in the sense that we have a small computer. There are 2 nuclear magnetic resonance computer for education are in the bottom right. These 2 devices over there are small computers for education. And I also try to teach how to introduce quantum computing in the core of the university curriculum, like a computer science or computing engineer, informatics, and so on, and not to produce professionals in that, but to have the basics understanding of that field. The field that I'm working now is in research is geometric properties, phases, and correlation of non-classicity in systems. I'm doing quantum computer to characterize these systems and then go from the domain of non-classicity, entanglement, and discord, which are quantifiers that make what a system is truly quantum. And this is the basis and to do more focalized algorithms in quantum machine learning that usually use truly quantum features. And this is an active research area in terms of how to make these properties in systems without opening, in the sense that there are an environment inside of them and try to produce the properties in a quantum computer and then to understand these systems in time. So aligned with this symposium mission, well, I say that this idea of no-code model can be replicated, no, and ready to scale between both institutions. I mean, not just me, but the people who already use AI in some context on quantum machine learning, on quantum computing, on quantum microelectronics, to see the experience, how these things is being used. And then after we have that, we have the opportunity to train and the next generation, but under this view, and then scientists and engineers with the basic quantum prompting, which doesn't mean that you have to be a proper quantum programmer. You need to have all the basic infrastructure of your field, engineer, whatever, and then use the tool in a proper way, and then you get into the field that you are working into your problems right away, straightforward in less amount of time. And also, but it is a way that I speak in the same language between the industry and academia, because the functional programming translate the lateral language in terms of solutions to the problem. And then you can say, I have this problem of optimization, this is my features and so on, use this algorithm and so on. So the way to do it is a more natural, and then the quantum formalism is more connected with the application. The training path is people who are just curious, practitioners, and also the orchestrator that solve specific problems and application on research. So proposed collaboration, a John No-Code Introductory Quantum Workshop. It's a national pilot session, virtual or hybrid, using this functionalized prompting model already developed, and also the experience that the people in the community has had in terms of using AI in the teaching or in an environment. Then move to the train from the idea of doing in a proper way, conceptualized with the prompting engineer adequately to the field, and focus in skills in areas of interest or applications, making a young applied research project, which is explore quantum machine learning oriented to microelectronics or metrology. For instance, in the right-hand side, I have using a prompt for classification. I use a data of 590 sensors measurement during semiconductor wafer manufacturing, predicting whether each wafer will pass or fail the quality control process. Dimensionally identify the effective part and see what the sensors are more important in terms of the feature of fail or pass. And this can be done in a matter of times once you have the prompting right properly and in terms of understanding what you want to achieve. This is a domain application for one side, and for the other side, the domain of the quantum machine learning and the classical machine learning embedded in the prompting properly, so that you get the information that is required in the domain application. This quantum machine learning can be connected with my field of research in terms of what makes a quantum algorithms have a quantum advantage. So you need to work out what are the quantum resources that are you use, such as this entropy Renai stabilization, quantum correlation, or this core, is affecting the advantage of doing the proper classification or optimization in the system, which is just an important practical area of interest and also an important research area in terms of the quantum machine learning and the definition of what is quantum advantage. Thank you very much.